Hello and welcome to this clip looking at the C3L6 2013 paper. We're going to be going through question 2 on this particular clip. So as per all my clips, this is not a mark scheme but just contains some ideas from me on how I might approach this type of question. It's always useful to have a copy of the paper with you, so that can be downloaded with the mark scheme and any exam commentaries from Cambridge themselves on www.c3l6.com. Now the box that they put at the front of every paper, just below the main title, tells you that some of the stuff in the booklet might be familiar, but other bits might be new. You might not have come across them before. All they're trying to do there is to encourage you to be a bit more deductive and take a more problem-solving approach, as opposed to maybe coming across something and thinking, I haven't come across this before, I haven't seen it before, help. So it's not going to be a factual recall paper in any sense. A bit further down, they talk to you about specifying your answers to the appropriate number of significant figures. That means the least sensitive from the question. Giving the correct units, and also making sure that you have the steps in your calculations that you've thought about, so that they can see the logic of your thinking. Quite often there'll be marks available for the method you use. Okay, so let's now have a look at the periodic table that this comes with. So it's also important to remember to use the actual periodic table provided with the paper, because it has a slightly higher number of decimal places. If you look at some of the values, there'll probably be more decimal places, 2 or 3, than the one that your exam board provides. So therefore the calculations that you're expected to carry out will assume that you're using the relative atomic mass values from this periodic table, not ones that you might have remembered from your exam board. So we start off by getting some contextual information that gives you what at first glance might look like just a bit of fluff at the beginning, but the context is useful because it tells you the reasoning behind the question and what the ideas that it's built on. But also, you never know, you might find something there that helps you in your thinking a little bit later on. I'm not trying to hint that there is something there in this particular case, but it's never a bad idea in a C3L6 paper. When they give you a body of text, almost always there is something there that is of use a little bit later on. So having a quick skim through the information preceding part A, it looks like it's going to be a fairly straightforward Hess cycle question. So it says, calculate the standard enthalpy change at 298 K for the hydrogenation of carbon dioxide, which is the reaction that they've given you. So the enthalpy data in the question is formation data because it says delta FH. So my box contains the constituent elements in their standard states in accordance with the definition of enthalpy of formation. However, hydrogen is in aqueous form in the reactant stage, so converting to this form from gaseous hydrogen, which is the constituent element in its standard state, we'll get an enthalpy value. So even though it's an element, I've put in an arrow here, which I've now highlighted in red so you can see what I'm talking about. So firstly, for each species we put in the molar enthalpy values and multiply these times the number of moles present. So starting with carbon dioxide, minus 121.0, then moving on to hydrogen. Hydrogen aqueous form is going to be minus 4.187, there's 4 of them, so that times 4. Moving on to methane, minus 89.10, and finally water, minus 286.0 times 2, all in kilojoules per mole. So following the dotted line as your progress of your reaction, the indirect route that is, and putting the numbers and switching the signs where appropriate, it gives you minus 523.352 kilojoules per mole to the minus 1. So part B introduces the idea of bacterial oxidation from Methylococcus thermopiles, as opposed to the oxidation by straight combustion of methane. So notice it says energy obtained. That's a clue. It tells you that the overall enthalpy change that you're about to work out is exothermic. That means it's got to be negative. So the equation for oxidation, complete oxidation in aqueous solution is exactly the same as the equation for normal combustion, except the state symbols are changed. Obviously you don't have CO2 as a gas, O2 as a gas, or CH4 as a gas. But liquid and aqueous can mix together, so you can still have water in the liquid form. So I put in my values for each species. I follow the dotted line, which is my indirect route. I put my species in their correct mole ratios and correct standard states in my box. So now I just work my way around. So that gives us minus 580.46 kilojoules per mole. So there's some useful information that talks about isotopes of xenon. It talks about determination of iodine. It talks about oxidation of iodide to iodine using nitrate 3 ions. It talks about extraction of iodine into hexane and reduction back to iodide with sulfate 4, followed by precipitation. So lots of different things being talked about. It also mentions mass spectroscopic analysis. So this would suggest that what they're doing is preparing the ground for a series of questions on this. So the first part of part C just talks about nitrate 3 and nitrate 5. It's probably that you're going to need this information as you go over the page and do the rest of part C. So if we take the Roman numerals to mean the oxidation state of the nitrogen in that particular ion, it should be quite possible to work out that nitrate 3 is NO2 minus and nitrate 5 is NO3 minus. So in terms of knowing that it happens to be negatively charged by 1, you'd be expected to know that the nitrate ion is NO3 minus from your work at GCSE and in the first part of the AS or first year A-level course. You'd also be expected to know that the Roman numerals denote nitrogen's oxidation state, so it shouldn't be too difficult to get these two formulae. So we can draw the structures out like that. In nitrate 3, nitrogen is using 3 electrons in bonding. And in nitrate 5, nitrogen is using 5 electrons in bonding. It might be worth pointing out, obviously, that we are now onto part II of part C. So it asks you to suggest the approximate bond angles in each. So what you've got to do is think about the lone pairs versus bond pairs. So for nitrate 3, there's 2 bond pairs including N double bond O. There's 1 lone pair. I've included the p orbital there to illustrate this. And that now means that it's based on a tetrahedral shape. Sorry, based on a trigonal planar shape. So that would mean that you'd have to take your 120 degrees and reduce the bond angle by 2.5 degrees, roughly. So your bond angle would be in the region of 117.5 degrees. And in the case of nitrate 5, it's regular trigonal planar, so 120 degrees. So because we're still doing part C, I've included the information from the previous page. So it asks me to work out the equation for the reaction between iodide and nitrate 3 ions. So I've left out spaces for the balancing numbers, but I don't know what they are yet, and I've put in the information that I know. So it also mentions oxidation, which means an increase in the oxidation number of iodide when it converts to iodine, so -1 goes to 0. At the same time, there has to be a reduction somewhere, so that means the oxidation number of nitrogen, the most likely other candidate, in nitrate 3 will decrease, so that means nitrogen will be reduced. So we need to put nitrogen on the right hand side because it mentions that in the information we're given in the question on the previous page. Because it tells us that in the information we're provided with. So nitrogen goes from oxidation state +3 in NO2 minus to oxidation state 0 in N2. which involves the gain of 3 electrons. So I- must lose 3 electrons when converting to I2. So if you take 3 iodides and you lose 3 electrons from it, you'll get 1.5 I2. So you have to get 2 iodine molecules ideally. So this gives us a total loss of 6 electrons, which must be accounted for in our reduction. In order to do this, we need to double the number of nitrate 3 ions, and in doing so double the number of nitrogens. So we can use charge balancing to deduce how many H plus ions are needed. They're a source of positive charge. So if you look at the negatively charged species, the reactant side has a net charge of -8, so 8 positive charges must be needed to balance this out. So finally we can use water on the product side to balance H pluses and O atoms from the left hand side. So from the text we know that iodine is reduced to iodide using sulfate 4 ions. So we're not being asked for an equation, it's just asking what sulfur containing ion will be formed. So if we draw out the half equation for the reduction they're talking about, you can see that the reduction requires 2 electrons. So remembering that sulfate 4 is SO3 2-, you can react SO3 with iodine by changing it to SO4 2-, which is sulfate 6. So obviously this would have to occur in the presence of water to provide the extra oxygen atom. So in this final part of part C, we use this information to combine the 2 half equations. So that gives us this equation here, which means we can now go on to part D. So this section starts talking about using radioactive decay as a method of estimating the age of the water sample, which will obviously be very, very old. We often use radioactive decay. For example, carbon dating uses carbon-14 isotope, which is radioactive. So some knowledge of subatomic particles from GCSE physics will be useful here, because if you see they're talking about alpha particles. So it's worth remembering that an alpha particle is the same as a helium nucleus, which obviously has 2 neutrons and 2 protons. So to help answer the question, I've taken the 2 sections of periodic table from earlier in the paper and just popped them up here in a bit bigger. So it asks which of the following statements may account for the production of argon 40 from potassium 40. So argon has 1 less proton than potassium, and because we've just recalled that an alpha particle actually has 2 protons, it can't be the emission of an alpha particle. So let's consider the number of protons and the number of neutrons that each of the 2 species has. Now in the second statement it says a neutron in the 40 potassium decays into a proton. To do this you'd end up with 20 neutrons and 20 protons. Now this doesn't match argon 40, so it can't be this one. So going on to the third statement, it says a proton in the potassium 40 decays into a neutron, a positron and a neutrino. So we can ignore the positrons and the neutrinos because they don't contribute to the mass as much as neutrons and protons do. However, the conversion of a proton into a neutron in potassium 40 would lead to 22 neutrons and 18 protons, so therefore that could account for the conversion they're talking about. So the fourth statement has the same effect as the second statement, so that can't be right either. The fifth statement has the same effect as the third statement, so that must be right as well. So let's move on to the next few sections. I think this is the end of the question actually. So it's time for the calculator again. So like I mentioned at the beginning of the clip, units, appropriate significant figures when asked for, and clear workings so the examiners can see what you're doing. So I need to convert my number of centimetres cubed of argon per centimetre cubed of water into decimeters cubed, because we're told that given that 1 mole of gas occupies a volume of 22.4 decimeters cubed at 0 degrees C. So if we take the number of moles of argon-40 and multiply that by the Avogadro number provided on the periodic table on this paper. Now the Avogadro number is the number of atoms in 1 mole. So therefore that gives us 1.196533482 times 10 to the power of 18 atoms of argon-40. So only the water contains the argon-40, and the rock is 1% water, which is contained in the pores. So working on the assumption that 100 centimetre cubed of rock contains 1 centimetre cubed of water, 2.7 grams is 1% of 270 grams. So it's that amount of rock that contains this amount of argon. So there's 2% by mass of potassium in the rock. So that would give us 5.4 grams of potassium. So it asks us to work out determine the number of atoms of potassium-40 in the mass of rock. So we have to remember that there's 5.4 grams of potassium in the rock. So we take the moles of potassium and multiply it by Avogadro's constant to get the number of atoms of potassium, including potassium-40 at 0.0117%. So taking that percentage into account, we can calculate it as 9.73180758 times 10 to the power of 18 atoms of potassium-40 present. So this next part introduces the decay constant of potassium-40. So this can be used to work out the age of the water. But only a small fraction actually ends up as argon-40. So the number of atoms of argon-40 is related to the number of atoms of potassium-40 remaining. So we want the actual age of the sample of water. So e to the power of the decay constant times time is the term containing time, which is what we actually want. So e is the base for natural log ln. So the photo shows where you can find the natural log button on your scientific calculator. So let's clear some space now to do our rearrangement. So we're looking for t from e to the power of lambda t minus 1. So let's rearrange in terms of e to the power of lambda t minus 1. So to get rid of e, you have to natural log the whole of the right hand side of the equation and then multiply by 1 over lambda, because you're inversing the power of lambda. So now we've got t. So we've now got the numbers subbed in. Let's just take a moment to track where these came from. So first of all, the fraction of potassium-40, which actually becomes argon-40. So now we have the calculated number of atoms of potassium-40 that you can see clearly below. The numerator is your calculated number of atoms of argon-40 in 1 centimetre cubed of water that we worked out a little while ago. We've got the 1 over decay constant for potassium-40. Decay constants provided on this page in the bottom left. So adding all the numbers in and putting the calculation through the calculator, we get 1.4 times 10 to the power of 9 years, or 1.4 billion years. So the calculator value is actually 13992222826. We put the exact values in because the values that we got are very slightly different to the values in the mark scheme, but we still end up with 1.4 times 10 to the power of 9 years. Okay, once again, thank you very much for listening, for sticking with us until here, and until next time, see you soon.